All right, so here are some tips for our assignment on the second part of chapter 2. I only had feedback from Caleb requesting having questions, very good list of questions. So thank you, Caleb. The rest of you, I hope you're getting along, but if you are stuck on any of the same problems Caleb was, I hope this helps. Okay, so his first question was on question 13, asking about question C. I think you probably meant 14 because there was no question C on it. So part C is finding this power function. And yeah, if you don't set up the power for each value, it's like, how do I find the function? So I'll explain that. So part A, we're looking at just the significance of this test, which says if S is less than 16, we're going to call it significant. So I'm going to, which this actually makes all the work easy. I found the significance level. If we have 16 or less on this binomial distribution, we're doing repeated trials, probability of success is 30%. I'm getting about 0.06 success, or you could use p-binom, which does the same thing. So actually in this lab, I'm going to switch to using p-binom because I want to make my work easier. So that's what the probability of success is, or the chance of successfully, it's the level at which we'll reject our our data. Okay, so then part B is saying the power of this test. So the power, I had to draw my whole table out. And so the power is the probability of rejecting the null given the alternative is true. So rejecting the null happens when S is less than 16. So we're looking at the probability of rejecting the null of S being less than 16 given that P is 0.025. Well, that's just p-binom, same thing we did earlier, except for now our probability is changing. So it looks like we have a 27% power. So part B is to help us for part C, because part B is just exactly the same thing, except for now our P is changing. It's saying use P is 0.02 up to 0.35. So I made this sequence of values. Whoops. So these are all the values I'm going to test my power for. And Caleb, what we mean by power curve is we're just going to find the power for each of these and then make a plot of it. So here's my power. I'm going to just find the power for each of those values of P. So I have these different powers for 0.02. If that's my alternative, if P is actually 0.02, we got a very high power. So if P is, you see it drops down. If P is 0.3, that's like somewhere here. We're going to have a very low power. We're not going to detect differences. Okay, so then I just put these on the curve. I got P, this is really the effect size, and then the power that I calculated. So there's my power curve. And so it's not really a function. I mean, I guess you could call this a function, p-binom, where this is like the input variable. So I guess it is a function, but more so we're just looking for what the power curve is, because this tells us, okay, now for various effect size that I'm trying to detect, what's the chance that I'm actually correctly rejecting the null. Okay, next question was it question 16? So I have to open up your question, Caleb. 16 said, you think you did the Wald type, but how do you do the two sample proportion for 16? So for 16, I set up my own Wald test for the two proportions, and I did my own scores test. And that way I could simulate the power quickly. So Wald test is just your standard difference of proportions. I got my p-value here. If I'm looking at greater, it's going to be 1 minus. If I'm looking at the alternative being less, it's just going to be the lower tail. So then the same thing for the scores test, except for here, what is it? What's different for my scores test? Trying to go back and see something. Oh yeah, the standard error is different. The standard error is calculated based off the values here, where the Wald test has the pooled proportion here. That's the difference. Okay, so it's different standard errors. So I'm going to think the wall test is going to have higher power, but let's see. And I tested this with the previous example. This is 315, so I ran my code. This should be the same examples you're getting for 315, and indeed the wall test was the same value. So I was just checking my functions. Okay, now I'm going to set up my power test. We got two different proportions we're sampling from. So an effect size of 0.1, and we're sampling of groups of size 50. And so R binom is how I can sample how many successes I'm going to get out of 50. That's right, one R binom n is 1 and P1 distribution. Yeah, that's how I do the binomial distribution. And it's 1. Okay, that's why I have that there. And then just to check, out of my big matrix, I have the mean of x1 is 0.599, so it's good. It should be close to 0.6. 0.50 is the second proportion, so it's kind of a sanity check that I'm sampling something that's reasonable. So now I'm going to do my power simulation. So for each row, I get a set of binomial samples. C1 is the total successes, C2 is the total successes for the second group. So the proportion of these should be something close to 0.6. The proportion of these should be close to 0.5. And so my wall test just takes the counts. So I don't need the proportions. I'm putting in the counts, and it's going to find my p-value for both of those. And after I run this, it's going to give me the power for each test. And indeed, the power for, oh, that's not what I expected. The power for the wall test is a little lower. Interesting. I don't know why that would be. But yeah, you can think about that. And maybe we'll get different answers. Maybe I should increase my B. Maybe I should run the test a little better. It's gonna take a while. So they're very close. That surprises me. The scores test doesn't take into account the null hypothesis that they're equal. But in any case, that's how you would do a power test for that. So then 17, question 17 is the same thing as this confidence intervals for difference of proportions. So notice you're looking at difference of what? Proportions between two front runners in a race. So that's this exact test. So it's also illustrated in example 2.7.2. So it's a very straightforward test. You just take your data and you got your two proportions and follow the procedure that's outlined here. So if you want to check your work, here's my confidence interval. It says there's no significance difference between the two front runners. Your next question was 18. This is a goodness of fit test. So for part A, we just took a histogram of our data. So this is data, and for part C, I think that was your question. Yeah, we want to test, is this the same as the binomial distribution? Is there evidence this is coming from a different distribution? So let's see. To get that, I'm going to make my binomial distribution. Here's the probability mass function for the binomial, given the same probability success we found in, is that right? Sample proportion. I think I need to put in the right sample proportion. Let's run this again. Oh, it's because there's randomization. I'm going to set seed here. I was getting different values, so I'm going to just set my seed at 0 if you want to compare your results with mine. Okay, so here is the actual proportion of successes. So I'm going to put that in here for my comparison now. So this probability mass function I use to get my expected counts. So if I'm going to plot that, this is going to show me, I should do a bar plot. X is 0 to 7. So no, am I doing wrong? Oh yeah, it's just one variable, and then I say names dot arg is 0 to 7. I think that should do it. Yeah, so that's my binomial distribution. This is what I'd expect to see if I were sampling from a binomial distribution, the same probability of success. And so, hey, are these different? They look kind of different, but the proper test for that would be a goodness of fit. So I could look at the difference of the observed and expected standardized difference to get me a chi-squared, and it looks like there's no evidence of a difference. Sorry, there is strong evidence of a difference. Excuse me. Yeah. And the chi-squared test approach also gives me the same statistic. So yeah, part of these questions is just sorting through what statistical test are we doing. And if we're looking at two different distributions, the table, the data for this, the observed data is, since it's a one-way table, that's a goodness of fit. We just have to spend a little bit of work looking at the theory of what would be the expected distribution if it was binomial. Okay, the next question is 18. That was 18. Question 18. So I just did. Okay, then question 21 was your last question, Caleb. So hint for this one, yeah, there's no data to test with. So once I wrote these functions, I did test it with data, but these are the exact same formulas as 2.24 and 2.26. So I found out for the P11 formula, that's 2.24. So here's my work for finding the counts for C11, the confidence interval, sorry, the confidence interval for P11. That's this. Here's my work for the confidence interval between the difference between P11 and P12. And so this is using the same confidence interval that was developed in, what page is that? I think I have the page here. You should be able to find it, but page 37. Yeah, so page 37, look at that. Oops, where am I now? So we are putting together a confidence interval based off some kind of contingency table. So I decided to test it with the approve and disapprove data from the previous problem, of course. So I use that previous problem, and it looks like I get answers that are comparable with what I got before. Oh no, it's a different test. So the confidence interval for this proportion is this. The confidence interval between the difference of these two proportions is this. Okay, anyhow, it works. I'm not sure really when you would do that, but it shows that all these tests can be generalized to different tables, and that is all. Sorry for the rambling. I hope that helps finish what you had remaining on this homework assignment and give you a solid foundation of all the categorical tests we can do with two-way tables and one-way tables. Very good. See you when I get back.